Hi everyone. We are still in the probability section of this course, and in this particular video we will introduce the ideas of counting. More specifically, we're going to be interested in discussing the addition and multiplication principles. As we've seen in previous videos, P of A, the probability that event A will occur, requires that we compute the ratio between the cardinality of A, where A stands for an event, and the cardinality of omega, the cardinality of the sample space. Now, more often than not, cardinalities for A and omega are actually not easy to compute, and certainly cannot be found easily by listing their sample points because they can be too numerous. So in this module, we will examine some basic counting methods, the first of which is the multiplication principle. Here's what it says. If there are n outcomes to a first experiment and m outcomes to another, then there are n times m outcomes to the two experiments. We use the multiplication principle when experiments are conducted in a specific order or within distinct categories. For example, you must answer two questions on a test. The first is a true or false question. The second is a multiple choice question where options A, B, C, D are offered to you. If you randomly select the answers to both questions, then here is the list of all possible outcomes. You could choose true with any combination of A, B, C, or D in the second question, or false in the first question with either A, B, C, or D in the second. Your answer to the first question can be considered a category, and the answer to the second as another category. You could also see each outcome as having a specific order. It's not surprising that the list of elements in the sample space is equal to 8 because 2 is the number of ways to choose between the options true or false. 4 is the number of options that you have when considering A, B, C, or D. And because your selections take place within two categories, the first question and the second, or in the true or false question and a multiple choice question, then the multiplication principle applies. So 2 times 4 is 8. However, if we considered the event A getting both correct answers, then the count of A, or the cardinality of A, would have to be exactly 1, because there is only one correct answer to the first question, and there is only one correct answer to the second question. The multiplication principle requires that you multiply 1 with 1. So the probability of the event, A, getting both correct answers, is therefore 1 over 8. Here's a much more elaborate situation. A license plate is to be made up of 3 letters, excluding letter O, so that we don't confuse it with the number 0, followed by 3 digits, which include 0 to 9. So there are 10 choices of digits. The number of license plates that can be printed obeys the multiplication principle since selections are performed in a specific order. For example, the license plate ABC 123 is certainly different from the license plate CBA 321. So order has its importance. Obviously, listing the possibilities is out of the question, but we do know that there will be a lot of them. You have 25 letters to pick from for all 3 positions where the letters will be placed. Because they are placed in a specific order, the multiplication principle occurs. Then there are 3 spots to fill with digits. And in each of these spots, we have 10 choices. Again, because this is done in a specific order, 10 times 10 times 10, the multiplication principle is used. If we consider the event A, where only vowels and odd numbers are obtained, then its cardinality can still be obtained by using the multiplication principle, since selections are once again performed in a specific order, or at least the letters and numbers must be placed in a specific order. This time we have some restrictions because we will assume there are 6 vowels, A, E, I, O, U, and we'll include Y just for the sake of argument. And there are only 5 odd numbers, 1, 3, 5, 7, 9. So the cardinality of A requires that we multiply 6 with 6 with 6, which are the optional vowels to be placed in the first 3 entries, and then the next 3 entries where we have a choice amongst 5 odd numbers to pick from. So 3 vowels to choose from A, E, I, O, U, 3 digits to choose from 1, 3, 5, 7, 9, and those selections are made in each 3 positions in the case of letters and in the case of the digits. So the probability that your license plate, if it is randomly printed, that it has only vowels or odd numbers is 0.17%. Suppose B represents that no letter and no number is repeated. This will also fall into the multiplication principle, but the restrictions will differ from those of the previous example. This time, the cardinality of B will be 25, which is the number of letters from which we can select. Keep in mind, we're still excluding the letter O. Regardless of the letter that was selected in the first position, there are 24 left to select from for the second position because we want no repeated letters. And then 23 are left in the next spot. So 25 times 24 times 23, because selections are done in a specific order, or selections are placed in a specific order. The numbers that are selected or printed on the license plate must also not be repeated. So from the digits 0 to 9, we have 10 choices. Once that choice is made, we have 9 left, and then finally 8. So 3 different letters are chosen, which explains the lowering of the values, and 3 different digits are chosen. As a result, the probability of event B occurring will be the ratio of the cardinality of B and of omega. And turns out roughly 64% is the probability of having a license plate with no repeated letter nor repeated number. The second principle we'll discuss is the addition principle. If outcomes of a random experiment are mutually exclusive, then the number of ways with which either occur can be added. You can apply the addition principle when one outcome or another satisfy the accomplishment of a particular event. Now the two occurrences must be distinguishable and have no common elements. Back to an example we discussed earlier. So let's review the situation where you have a true or false question followed by a multiple choice question with options A, B, C, D. We had said that there were 8 arbitrary ways or random ways to select those 2 answers, and our list is still provided here. So the size of the sample space with the cardinality of omega is 8. Now suppose B represents getting 1 correct answer, and I mean exactly 1 correct answer. It can be interpreted as getting either the first answer correctly or obtaining a correct answer on the second question, but not both. So we can find the cardinality of B by using the addition principle, where in the first calculation we have counted the number of correct answers to the first question followed by wrong answers to the second. So there's only 1 correct answer between true or false, and there are 3 incorrect ways to choose an answer for the second question. Or perhaps we have the correct answer on our second try, there is one possible wrong answer to the first question, and there is only one possible correct answer to the second. So 3 ways to get the first question correctly, and only one way to get the correct second answer correctly, and that would add up to 4. In both cases, I'm excluding the possibility of having both correct answers. For instance, a license plate is made up of 3 letters, excluding O to avoid confusion, and followed by 3 digits, or vice versa. So the number of license plate that can be counted using the addition principle. So we're going to count all the ways to print license plates, starting with 3 letters, and then count all ways to print license plates that start with 3 numbers. So here are the number of ways to print license plates that start with 3 letters. So 25 choices for all 3 spots, followed by 10 options for all 3-digit spots. Or then we can print license plates that start with 3 digits, from which we have 10 to choose, then which will be followed by 3 letters, from which we have 25 to choose. Okay, so we have here our addition principle. Here's an applied situation. We have a lottery that proceeds in the following way. 5 containers all have 9 balls labeled 1 to 9. A ball is randomly selected from each container in a specific order to form the winning number. So the number of possible outcomes is using the multiplication principle, 9 times 9 times 9 times 9 times 9. Since for every container 9 possible outcomes occur, the numbers that we select are placed in a specific order, so that's the multiplication principle. A $5,000 prize is awarded to a participant that has a ticket with the winning number, so the exact right numbers in the exact right positions. A $1,000 prize is awarded to a participant whose ticket has a string of 4 correct numbers. And $200 is awarded to a participant that has a string of 3 correct numbers. For instance, if the winning number is 1, 2, 3, 4, 5, someone whose ticket has numbers 7, 2, 3, 4, 5 would earn $1,000 because he or she has a string of 4 correct numbers. A ticket with numbers 7, 2, 3, 4, 9 would earn $200 because this time we would have a string of 3 consecutive correct numbers. So those are the rules. The number of ways to win the lottery is obvious here. There's only one way to have every correct number. So 1 times 1 times 1 times 1 times 1. And that would give us a very low probability of winning, as you can see. When it comes to the number of ways of winning $1,000 though, well, there are 2 ways or 2 options we can consider here. So either we have the last 4 digits correct, or the first 4, and that's what I've split up. The first number has to be an incorrect number, so it's any 8 that was not selected when the ball was drawn. Or the last number has to be incorrect, which is if the last digit on our ticket is wrong. So either the first is incorrect or the last is incorrect. That's the addition principle. And so the probability of winning $1,000 is 16 over 59,049. So 16 being the 8 plus 8. The number of ways to win $200 splits up into possibilities where either the first 2 numbers are wrong, which leads to 3 correct numbers consecutively, or the 3 middle ones are correct with incorrect numbers at the extremities, or the first 3 are correct with 2 ending numbers that are wrong. In this case, we would find the probability of winning to be 192 over 59,049.